Why is quantum magnetometry sensitive to noise? Imagine trying to listen to a whisper in a noisy room. That's similar to what quantum magnetometry faces when detecting tiny magnetic fields. It uses special quantum states to measure magnetic fields with incredible precision. But these states are very fragile. External disturbances or internal imperfections can easily disturb them. That's why noise becomes a big challenge. Quantum magnetometers work by preparing quantum states, letting them evolve under the influence of magnetic fields, and then measuring the final state. The goal is to see how much the magnetic field changed the quantum state. But maintaining the coherence of these states is tricky. Noise can cause decoherence, which means the quantum states lose their special properties. When that happens, the measurement becomes less accurate. There are two main types of noise that affect quantum magnetometry. The first is quantum noise, which comes from the fundamental rules of quantum mechanics. For example, spin projection noise is the uncertainty in measuring the spin of particles, and photon shot noise is the randomness in counting photons in optical measurements. These are limits set by nature itself. The second type is technical noise, which comes from outside sources. This includes temperature fluctuations, electromagnetic interference, and imperfections in the equipment. For instance, thermal noise can cause random changes in the quantum system, making it harder to get a clear signal. Electromagnetic interference can mask or distort the magnetic signals you want to measure. Because quantum magnetometers often operate near these fundamental limits, even tiny amounts of noise can significantly reduce their sensitivity. When entangled states are used to boost measurement precision, they become even more vulnerable. Decoherence can break entanglement, which means losing the quantum advantage. To fight noise, scientists use several strategies. Cooling the system to very low temperatures, called cryogenic cooling, reduces thermal noise. Using squeezed light, which manipulates the uncertainty in light measurements, helps lower shot noise. Active feedback control systems constantly monitor and adjust the quantum states to counteract disturbances. Researchers are also developing quantum error correction codes to detect and fix errors during measurements. Optimizing the design of the system, like the arrangement of atomic spins and timing of measurements, can make it more resistant to noise. Even with these efforts, noise remains a challenge because it limits how sensitive the measurements can get. But ongoing research shows that, with careful design and control, quantum magnetometers can still outperform classical sensors in noisy environments. This makes them promising tools for applications like brain imaging, exploring fundamental physics, and navigation. In short, quantum magnetometry is sensitive to noise because the quantum states that give it an edge are delicate. Both quantum and technical noise sources can interfere with the measurement process. However, advances in noise reduction and error correction are helping these sensors become more robust, opening up new possibilities for their use in real-world situations.